transformations in 2 dimension or in 2D. Well, 2-dimensional transformations and the use of linear algebra or matrix theory are almost very interlinked. In fact, for the first hour today, we are going to have in this course a quite little bit of mathematics, I should say, which is necessary to understand about 2-dimensional transformations, matrix manipulations, mainly to do with multiplications and additions, a little bit of inverse, transpose, properties of matrices you must know, I believe. And if you have not probably touched upon it in the recent past, I will advise that you go back to your basic mathematical books or computations in engineering, let us say, and look back into concepts of matrix and properties of even determinants, matrix manipulations, and simple things like that. Okay, so we are talking of transformations. So if you look here, we are talking about representation of a point in a 2×1 matrix. That means it is a column vector with 1 column and 2 rows. The 2 corresponding elements in the column are just the x and y coordinates of the matrix. We assume in a graph paper the origin in the left bottom and there is a point x and y, so that is also a matrix form it is represented, and you are going to apply transformation onto this point. We are going to move it anywhere on the screen depending upon where you want. You could move a line or a point or a structure, and we need to see how to apply these different type of transformations using basic matrix theory or using matrix manipulation techniques. So, well, the general method of implementing a transformation is to apply operator T, which is again a matrix, on the operator A. A is the coordinates of the points or point, let us say, on which we are going to apply the transformation, and T is the operator matrix, and the multiplication of T with A gives you the position of the new point or points B. So that's the basic idea of transformations. It's basically matrix manipulation I was just talking about, is what you have to know. Okay, so the T, we will say, represents a generic operator to be applied to the points in A. A could be a single point or more than one point, we will see, because we had seen in the concept of raster refresh graphics displays that typically when we have to draw objects including lines, polygons and areas, typically all those are built up with points. Okay, it's a mixture of points, and so we want to transform the object, we have to transform all these points, because the shape information must be kept almost intact in general. Of course, there are certain cases where the shape information also may not be intact after the transformation takes place. So we apply the T on point or points in A, and T is called the geometric transformation matrix. It's also called the affine transformation matrix. In general, where it depends upon what functional form you are using, you might get different type of transformations. So the right hand side of the equation B equals TA is known, and if A and T are known, the last line as it says, then the transform points are obtained by calculating B, and the points in B, which are the transform points, are obtained by a simple matrix multiplication of T with A. General transformations of 2D points. Before we move forward with the different types of transformations, I would like to give you another a little bit of insight to this matrix multiplication. There are 2 ways you can multiply a matrix. Either put the matrix B equals AT, we can sometimes say even T A instead of AT. Well, if you look into the general form of matrix multiplication here, we are talking about xy, the point coordinate in the graphic screen, which is pre-multiplied. Why pre? Because this operator T, which has 4 parameters, the scalar 4 elements of the matrix T are A, B, C and D as given here. and if you pre-multiply, you get the new coordinates or transform coordinates x prime and y prime. If you know the matrix multiplication, which is obviously very simple, you can easily see that the equation, first you get two equations, two linear equations, scalar equations I will say, from the vector or the matrix multiplication equation here, where x prime, the transform coordinate, x coordinate of the transform point is ax plus cy, and the y prime is bx plus dy. Okay, so if you multiply, you get this, as you can see, row and then column multiplication. The x prime is ax plus cy, and if you take the bottom row of t and the column of the x, that is we have y prime equals bx plus dy. Okay, so that is what you typically see. I can represent this transformation, as you see here, by a different order of multiplication. Okay, if you look into this, on the right hand side, I am saying that the coordinates of a point P given as x comma y is now being post multiplied. Okay, this difference between post and pre multiplied. The operator T is now on the right hand side of B. In the previous case it was left hand side, that means it was pre multiplied. In this case it is post multiplied, but of course you must be careful here of two things, that we are saying that the coordinates of a point P given by x and y, or x prime or y prime, is a row vector. You see the transpose sign on top of the of x and y and x prime y prime on the equation given on the right hand side block, and so we are talking of a row vector. And to keep the consistency of the equation in terms of the interpretation of A, B, C, D, the four elements of the operator matrix T, what you see now, that the position of the elements, especially the off diagonal elements B and C, have been changed in T. Okay, you just see, please notice that the equations in terms of x prime equals whatever and y prime equals whatever, ax plus cy and bx plus dy, that equation is kept unaltered. And to keep that unaltered and to handle both forms of pre-multiplication and post-multiplication of the point coordinate P with the operator T, two changes have to be made. First of all, the column vector of the point coordinates becomes a row vector, and the matrix T is basically a transpose of the previous matrix, because the diagonal elements are there wherever it is A and D. B, C have interchanged positions, so it's basically it's a T transpose, it's a transpose of the matrix. So you can use any one of these representations given either on the left hand side or on the right hand side, is absolutely no problem. And I should mention here that some books follow the left hand side or the multiplication notation, some books on the other hand follow the post multiplication, pre and post, but you should actually keep a watch on what form you are using, what you are comfortable. You can use any one of them, but never mix. Never mix in an equation when you are using it for implementation or deriving anything analytically. Please do not mix up the representations of pre and post multiplication. You can use interchangeably any notation you like in terms of pre or post multiplication, but be consistent. Be consistent in the sense that if you start with pre-multiplication, follow the pre-multiplication representation of matrix multiplication to implement geometric transformations throughout your derivations or program implementation. Whereas if you are starting with the post multiplication transpose and all that, you better also stick to that. Please don't keep swapping. In the course I have probably tried to stick to this, but once in a while I will probably bring in the other example also to just give you an idea of what is the little difference. In terms of implementation and the end result, it is all same. All same. Why? Because you see the expressions here, x primes equals and y primes equals whatever is given is the same. The corresponding coefficients of x and y after transformation is ax, a for x and b, and c for c and d for y respectively. That is kept unaltered, because if you keep that unaltered, the significance of the elements a, b, c, d, four elements of the operator T will remain the same. Their significance, their method of whatever they are going to transform is going to remain unaltered, whereas in terms of matrix you can either use post multiplication or pre multiplication. There is absolutely no problem, but again I keep repeating this, that you must follow it in a methodical manner. Well, the other point about general transformations of 2D points is the following, that we are only going to discuss in this course and obviously in the lecture today and the next one and the remaining lecture on transformations whenever it comes. Of course, after 2D we are going to 3D transformations, all right, but even in 2D as well as in 3D, we are going to discuss solid body transformations. As you see in the slide here, we're going to talk about solid body transformations. That means the above equation, whichever you pick up, left or right, pre or post, is valid for all set of points and lines of the object being transformed. That means when you transform an object from one position to another and give it any sort of transformations, we say that the transformation equation is applicable for not only the entire object or the object by itself, but all points or lines, whatever you trace on the object. It's also valid for all those points. And solid body talks about that the body doesn't change its shape or size in general. Okay, and it's a solid body in the sense that the corresponding displacement or distance between any two points, if you draw a line on a solid object before transformation and then transform it, okay, you start at one point and then transform it to another point, the inter point displacement or the distance between any two points is going to be invariant with this transformation. That's the meaning of solid body transformations. Any solid object, you will follow these rules and norms. Of course, what does it mean? What is the other part of the world? Yes, we are talking of deformable object structures. Typically, it could be a cloth, it could be a paper, it could be a rubber sheet, and there are a few examples of those. Any soft products, sponge, let us say, those are examples of deformable structures or non-solid objects. We are not going to discuss about those because that is a separate area by itself. It's in fact area of big research to represent those transformations of non-rigid structures, represent transformations as well as deformations of those structures. But what we are going to discuss only is solid body. Correct? You take on any object, it could be a deuce ball or a cricket ball being played on the field to the normal table chair, whatever you see in front of us. All solid objects undergo transformations, and in the transformations, the entire object as well as all points and all lines, curves which you draw on the object will basically follow the same pattern of transformations, and the object will not typically change its structure except in one particular case. But in solid object, typically we assume that the body doesn't change its structure, although transformations in some cases may appear to change the structure. Okay, we'll look at some special cases of 2D transformations. The most simplest one, you remember the transformation matrix G, correct? And the case when the diagonal elements, you remember the structure A, B, C, D. Okay, it will come back again that form. When the diagonal elements A and